Hi, this is Yun-Chun. In this video, I'm going to talk about occupancy networks. 3D reconstruction is a task that aims to reconstruct the shape of an object. Voxel representations are a straightforward generalization of pixels to the 3D case. Unfortunately, the memory footprint of voxel representations grows cubically with resolution. Point cloud representations have been introduced. However, the lack of connectivity structure requires additional post-processing steps to extract 3D geometry from the model. There is also another alternative representation called meshes. Existing mesh representations are typically based on deforming a template mesh and hence do not allow arbitrary topologies. In this paper, the authors propose a new 3D representation based on 3D occupancy. The network is trained to predict the occupancy with a neural network, which can be evaluated at arbitrary resolution with a constant memory footprint. Occupancy networks represent the 3D geometry as the decision boundary of the classifier that learns to separate the object's inside from its outside. The goal is to learn a nonlinear function that takes as input a 3D point and predicts its probability of occupancy. Once the network is trained, the decision boundary represents the object's surface. Given a visual observation of an object in voxels, point clouds, or images, as well as 3D coordinates, we first compute an embedding C of the input. Then we feed the input points through an MLP network. We use conditional batch normalization to condition the network on the embedding C. To train the network, we compute the cross-entropy loss between the predicted occupancy and the ground truths. To extract meshes at test time, this paper introduces a method that enables us to extract high-resolution meshes from the occupancy network without having to densely evaluating all points of a high-dimensional occupancy grid. The initial mesh extracted by marching cubes can be further refined. To address this paper uses an off-the-shelf mesh simplification method to first reduce the number of vertices and faces. The simplified mesh is then refined using first and second order information. Occupancy networks performs well on single image reconstruction from synthetic images. In addition, the authors also evaluate on 2D real images and showed that occupancy networks also performs well in this setting. Occupancy networks can also be applied to point cloud completion. Given a noisy point cloud, the goal is to reconstruct the mesh. Quantitatively, occupancy networks perform the best. This paper proposes a new representation for 3D geometry. The proposed method is not constrained by the discretization of the 3D space and can hence be used to represent high-resolution meshes. Experimental results demonstrate that occupancy networks are very expressive and can be used for various tasks and settings. Thank you.